is continuous on a comma b, differentiable on a comma b open interval. It doesn't have to be differentiable at the endpoint, but this is mandatory. F of a must equal f of b. Therefore, we can conclude that the function has to have at least one term, at least one. It could do this. So we will have more than one term. Doesn't have to be a max or a min, but at least one term. Okay, so before we look at the mean value theorem, I'd like to look at a problem. Let's say on page 289, yeah, why not? Let's look at 11. F of x equals natural log x and the interval 1, 4. Verify that the function, oh no, I jumped. Verify that the function satisfies the hypothesis of the mean value theorem. So this has to wait. I'll come back to it. Let's look at 3. So f of x equals the square root of x minus 1/3 x on the interval 0, 9. Verify that the function satisfies the 3 hypotheses of Rolle's theorem on the given interval. Then find all numbers C that satisfy the conclusion of Rolle's theorem. Where do I start? What do I have to write? Yes. How do I know that, number one, that f of x is continuous on the interval 0, 9? Very good. And this is a linear function continuous everywhere. As a difference of 2 continuous functions, square root and linear, on the interval. Excellent. Number 2. So f of x is differentiable on the interval at least 0, 9. And actually, the square root is not differentiable at 0. It has a vertical tangent. So f of x is differentiable on 0, 9 as a difference of 2 differentiable functions. Now I need hypothesis number 3, without which I can conclude or I cannot apply the theorem. What is the third hypothesis? That f of 0 and f of 9 are the same. So when I plug in 0, I get 0. And when I plug in 9 in this function, the square root of 9 is 3. 9 divided by 3 is 3, and 3 minus 3 is 0. Therefore, all 3 conditions are fulfilled. Function is continuous on 0, 9, differentiable on open interval 0, 9, and f of 0 equals f of 9. What do I conclude? There exists a C, at least one, in the interval 0, 9 such that is 0. So I have to find f prime of x first. So f prime of x will be 1 over 2 the square root of x minus 1/3. Now f prime of c will be 1 over 2 the square root of c minus 1/3, and I have to set this equal to 0. I don't like writing it here though. So 1 over 2 the square root of c minus 1/3 equals 0. I move 1/3. 2 fractions are equal and they have the same numerator. What has to happen to their denominators? They have to equal each other. If the fractions are equal and they have the same numerator, they must have the same denominator, or you cross multiply. So 2 the square root of c must be 3, or the square root of c equals 3/2, or c must equal. Now I have to make sure that 9 over 4 is where? Between 0 and 9. Of course it is between 0 and 9, but just making sure always. Make sure that you didn't make a mistake or you got something else. So, and I'll say, I should have written it here, by Rolle's theorem. It's guaranteed by Rolle's theorem because the following conditions are fulfilled. Continuous, differentiable, f of 0 equals f of 9. The function must have at least one term. So there must be at least one c. I can have more than one, but at least one, for sure. Any questions? Any questions?
How would we know there's more than one?
Oh, I will get plus or minus, or I will get a cubic function, a cubic equation with 3 solutions, or I will get a 4th degree, whatever.
Is there one that we can work through?
I'm not sure.
It's very easy to, I guess, number 2 probably.
Number 2? Yeah, you want to work on this? Yep. So let's look at number 2. So, and number 2 we have, so this is 2 on page 288. We are given f of x equals x to the 3rd minus x squared minus 6x plus 2 on the interval 0, 3.
So,
Yes.
this is just this is just something that I was kind of wondering.
Yes.
With the, to me, it seems like the mean value there was like an extension of the Rolle's.
Of course.
So
With even less hypothesis, less requirement. Yes.
So I know that this is kind of an odd question. Is there a sort of a specific reason that we don't just drop Rolle's and
Yes.
use the
Very good question. So you're basically asking what is the difference between applications of Rolle's and applications of, okay. Rolle's theorem has a wider applicability than Rolle. A mean value theorem has a wider applicability than Rolle's theorem. So there are specific situations under the big umbrella of mean value theorem. There is a category that fit in for Rolle's theorem. Yeah. Sure. Did we get it? Do we need more time? If yes, I'll take attendance.
Yes.
Okay. Because if I don't, while you're here, I forget. Okay, can I start? So first I have to write, number 1, that f is continuous on the interval 0, 3 as a polynomial function. Step number 2, f is differentiable on 0, 3 for the same reason. All polynomial functions are differentiable everywhere. Step number 3, I have to find f of 0. 0 is 2, and I have to find f of 3, which is, bless you, 27 minus 9 minus 18 plus 2. It's 2, correct, yes. These are 0. Therefore, all 3 conditions or hypotheses of Rolle's theorem are fulfilled. So then I'll say then f prime of x is 3x squared minus 2x minus 6. So there is f prime of c that will be 0. Or 3c squared minus 2c minus 6 equals 0. Of course, I will use, quadratic formula. Negative b plus or minus b squared minus 4ac divided by 2a. So this is 76. Okay, I'll punch it in the calculator. So left parenthesis, 2 plus the square root of, isn't it? That's 72, right? 76, correct? And I divide by 6. And then the other one, good. So I got 2 options. But since the interval is 0, 3, only c equals 1.786 and c equals negative 119 is not in the interval 0, 3. Any questions? Any questions? Okay. So I understand that this was not exactly what you expected, but it can happen. We can have at least, or we can have more than one C. I'll try to find an example in which we get 2 solutions. C1 equals whatever and C2 equals whatever, and they're both in the interval 0, 3, or whatever interval. Okay? Good. So now let's look at a more general case. Bear with me. So this is a function f of x. Is this function continuous on the interval a comma b? So f, number 1, continuous on a comma b. Number 2, is f differentiable at least on the interval a comma b? No corners, no cusps. Okay, very good. Then I'm going to denote this point by A and this point by B. Can anyone give us the coordinates of A?
It's little a, f of little
Good. And this? Good. So then we do have A of A, f of A, and we have B of B, f of B. We agree with that. So please watch for a second. I will draw a secant line, nothing to do with a trig secant. So this is a line going through A and B. And next I'm going to do this. I'm going to draw a line that is a tangent line parallel to this one. So I'm just shifting the line AB till it becomes a tangent. So at this point, I hope you agree. That's another point. I'm going to call it C with lowercase c. And can anyone give us the slope of this line? So I'm going to call it line 1. And can anyone give us the slope of line 1?
It should be the difference quotient over FB minus FA over B minus A.
Also, this is also the same with,
C. Well, you're talking about the line.
I'm talking about the slope. The slope of this line is the slope of this line. That's why we used f of b minus f of a over b minus a, but there is another way of determining the slope of line 1.
Take that C for tangent minus C.
I can only cheat read it out of the book.
What should it be? We know that. We've been using this over and over. We already used that. y2 minus y1 over x2 minus x1. We used that.
Oh, so F prime of C.
That's it.
Okay, that's not what was in the book. Okay.
Of course. Of course. It's the tangent line to the graph of a function at a point. It must be f prime of c, correct? Yes? So, one more time. If you forget about this for a moment, and I just ask you, what is the slope of the tangent line at this point? Forget about AB. What is the slope of the tangent line at this point? You will have to say f prime of z. Correct? Okay. So now, this is the conclusion that we obtain from the mean value theorem. So if a function is continuous and it's differentiable, we don't even care what type of function it is, it's continuous and differentiable, then there must be a point on the graph whose derivative is given by the slope of a secant line that crosses the graph in 2 points, or the average. This is also the average rate of change between A and B, which is a powerful result. So let's see how we apply this. So this is the mean value theorem. By the mean value theorem. So if a function is continuous and differentiable, we will always be able to write this. Of course, there is another way of writing it, and here's another way, like f of b minus f of a equals, I cross multiply, f prime of c times b minus a. And I know you know this. If I move f of a to the other side, do you remember this? The linearization. Exactly. Exactly. Very similar, right? Oh, it's all the same. Okay, so now, if you remember, I copied 11 by mistake. And let's go back to 11. When was it? Like half an hour ago? Okay, here it is. So we have, in number 11, we are given f of x, which is natural log x, and the interval 1, 4. So let's see. So we are given an interval, and we are basically told, show that there is a c in the interval 1, 4, that whose derivative is the same with the average rate of change of the function between 1 and 4. That's basically what it says. So how do I start? What do I have to write first? It says apply the mean value theorem for this function on the interval 1, 4. So first I have to write it's continuous. Number 1, f of x equals natural log continuous on 1, 4. How do I know the natural log is continuous? Natural log is continuous on all its domain. Number 2.
It's differentiable.
Yes, looking at the graph, I know it's differentiable between 1 and 4. F of x equals natural log is differentiable on the interval 1 comma 4. Any function that is continuous and differentiable on an interval will fulfill the mean value theorem. Therefore, f of 4, yes, I should have written, therefore, I should say, there is c in the interval 1 comma 4 such that f of 4 minus f of 1 equals f prime of c times 4 minus 1. You can say I don't like this, but I like this. That's fine too. It's the same thing. Here I just cross multiplied. So function is continuous, differentiable, continuous on 1, 4, closed, and differentiable on 1, 4. So therefore, there must be a c in the interval 1 comma 4 such that f of 4 minus f of 1 equals f prime of c times 4 minus 1. I have to find f prime of c by finding f prime of x first. When I differentiate natural log, I get 1 over x. Well, when I have f prime of c, I get 1 over c. So I have to find f of 4. Well, f of 4 is natural log 4 minus. How much is natural log 1? 0. Perfect. Equals 1 over c. How much is 4 minus 1? Cross multiply, or just swap these two. I'm allowed to do that. So then c equals 3 divided by natural log 4. And the answer, when I punch in the calculator, it better be where? Between 1 and 4. So when I divide 3 by natural log 4, I get 2.16. So c approximately 2.16, which is indeed in the interval 1 comma 4. Questions?
And so Rolle's theorem is just a specific part of that.
Exactly.
That's what you were saying.
Yes, exactly. Under a bigger umbrella for the functions that work with mean value theorem, there is a specific special category, because here there is no need for f of a to be equal to f of b. Can be any. Can they be equal? Yes. Any questions on Rolle's theorem and the mean value theorem?
Is it about the mean value theorem?
Yes, of course. Please choose. Let's do 13. So we have f of x equals the square root of x, and the interval is 0 comma 4. So we have a function, and we want to determine c such that it's satisfied by, because the function satisfies the mean value theorem hypothesis. So there are only two hypotheses here, and then we can go ahead and find c. So the first step is I have to write that f is, I guess you need more time. Okay, so f is continuous on the 0, 4 as a square root function, which is continuous everywhere, where it's defined, of course. F is differentiable on the interval 0, 4. It's not differentiable at 0, but we know it's differentiable at 0, 4. Therefore, MVT guarantees, what does MVT guarantee? A C in the interval 0, 4 such that f of 4, 2, f of 0, 0 equals f prime of C times 4. Okay, I will simplify and then move the square root of C to be 1. So therefore C equals, when you square both sides, just 1. When you square both sides, C is 1.
Oh, yeah.
That's okay. So indeed, C is between 0 and 4. Any questions? Any questions? I'm not going to start section 4.3, but I just want to mention one thing about section 4.3, and we'll start it on Wednesday. Just allow me 2 minutes and then I'll stop. Promise. Remember my chart. F prime, then in the middle f of x, and then at the bottom the second derivative. Right? So what does the first derivative tell us about the function? Quite a lot. It tells us where the function has a max or a min, because the derivative is either 0 or undefined. So for example, this function is continuous, but it's not differentiable at this point. So it's not differentiable, but it still has a maximum at that point. So the derivative tells us whether the function has a max or a min when the first derivative is 0 or undefined. Also, it tells us when we study the sign of the derivative, it tells us whether the function is increasing or decreasing. If the first derivative is positive, the function is increasing. If the first derivative is negative, the function is decreasing. That's all it is what the first derivative is used for, right? It gives us max, min, and increasing, decreasing. Now, what am I going to use the second derivative for? Because I'm going to use the second derivative. I'm going to differentiate, find f prime, and then I'm going to differentiate and find the second derivative. So the second derivative gives us what it's called points of inflection. Here's a point of inflection. Right here. What happens at this point? From changing, it changes concavity. From opening downward, all of a sudden, it changes concavity and opens upward, or vice versa. Those points will be given by the second derivative. So the second derivative has to be 0 at this point and change sign. Now, one thing that I'll stop. Let's say at x equals 1, I know the first derivative is 0, and I know that, I know that the second derivative is positive. Let's just analyze this situation. This is not about the sign. Okay, so I know that the first derivative is 0 at a particular point, and I know that the second derivative is positive. When the second derivative is positive, the function opens upward. What type of point is this? Now, I did not study the sign of the derivative. I don't know if it's positive, negative, or negative positive. But I know that the first derivative is 0, and I know that when the second derivative is positive, the function is concave upward. So what point is this, for sure?
Local or absolute minimum?
Absolutely. What if I know that the first derivative is 0 at 1, but this, the second derivative, has a negative sign, which means the function opens downward. And at this point, somewhere in the middle of the interval, the first derivative is 0. What will that represent? And that is what we call the second derivative test. So at some point in time or some situations, you'll say, oh no, I don't want to study the sign of this. Maybe it's easier to study the sign of this. But I know that the derivative is 0, and I know that the second derivative is negative, so it must be a local or absolute max. Okay? So in 4.3, we're going to add the second derivative and discuss a little bit more about this first derivative test, which we already exhausted, but we will look at the examples. Then we are going to add the second derivative, and then we're going to practice, and we will be able to graph any function you can think of without the graphing calculator. We will be able to find everything about it. And that will pretty much be the end of chapter 4. But we have to practice. And I have 2 more sections at the end that there are other applications. And I'll talk about those on Wednesday. But we're going to stay here for at least 2 sessions and graph these functions from the beginning till the end. And then finalize optimization in Newton's method.